Okay, back to more on functions and their graphs. We have some objectives listed there at the top. Difference quotient, piecewise functions, increasing, decreasing, constant, even and odd functions. Those are our focuses this unit, and how to determine or understand or identify them. Let's start with the difference quotient. I cannot emphasize enough how important this is for those of you going on to calculus. I have so many students struggle with this in calculus, and we see it there as basically the foundation of one of the most important things of calculus. So I really want to emphasize to you how important this is if you are going on to a calculus course. Okay, here's what it is. The difference quotient is equal to f of x plus h minus f of x all over h. That's it. Yep, super important. I know it doesn't look like it or seem like it would be, but it is super important. So here's the question. We got our question face guy here. Why would we want to know the difference quotient? Well, let's think about what it represents. If we are looking at a function, let's suppose, let me just draw a function kind of like this, whatever your function looks like. Let's suppose this is some x value. This right here would be f of x, right? That y value that goes with that x value. Let's suppose we go some distance, we walk out over here some distance of h. That makes this x value right here x plus h. And if we go up here, over to here, this is f of x plus h. Okay? So what the difference quotient actually gives us is, and this is something that is actually taught in this class in the next unit, calculating the slope of a line, but I think most of you have seen it. If you remember, so we're going to do a little preview for what's to come. Slope is equal to rise over run, or the change in the y values. You may have seen it as y2 minus y1 over x2 minus x1. If you connect a straight line from here to here, the slope of that line is equal to the difference quotient. Because if it is the change in y values, it is this difference between those, which is f of x plus h minus f of x, divided by the change in these values, which we know is h, or you could look at it as x plus h minus x. The change, subtracting the y values, just simplifies to the h, but it's the distance between them, which we set to be h. And so the idea is that if we want to go along a function and some maybe unknown distance h and go out there and then see the slope of the line that connects a couple of points, that's exactly what the difference quotient gives us. You will see the huge applications of this in calculus, but that is sort of the preview of that. Okay? Let's actually find the difference quotient for a function. Remember, our definition is f of x plus h minus f of x all over h. That is going to equal, okay, what do we mean when we say f of x plus h? Remember the smiley face? Everywhere you see an x in the original function, you need to replace it with whatever is inside the parentheses. In this case, x plus h. So I write my 3 down. I replace that x with x plus h. That first part that I just wrote there, that is my f of x plus h. Wherever I see an x, I replace it with x plus h. Pause the video right now if you need to think about that a little bit. This is sometimes very confusing for students. That's the first part. Then we subtract the function itself and divide by h. Now we need to do some algebra to clean this up. X plus h, quantity squared. Remember, that means x plus h times x plus h. It does not mean is not equal to x squared plus h squared. Another common mistake I see. You have to distribute it out. You get x squared plus xh plus xh plus h squared, x squared plus 2xh plus h squared if you combine your like terms. So that replaces the x plus h quantity squared. Just distribute it out, the x plus h squared. Now I'm going to distribute my negative. And now I'm going to distribute my 3. 3x squared plus 6xh plus 3h squared minus 2 minus 3x squared plus 2 all over h. We're getting close here. We got to simplify as much as we can. What do you notice here? 3x squared minus 3x squared is 0. So those simplify. And negative 2 plus 2 simplify. Here's a hint. A lot of stuff should simplify away when you do this difference quotient. All of your function at the end there, the x squared should be. If you didn't, you forgot to distribute or something. 6xh plus 3h squared is all we have left in the numerator, all over h. Still not done. I can factor out an h so that I can simplify it, giving me a final answer for my difference quotient in its most simplified form of 6x plus 3h. Is the difference quotient. Seriously, pause the video, scroll back through, make sure you understand all the steps that we just did there. This is the most difficult thing that students struggle with on the first test. Every time I can look at the analysis of the test, it is always the one that is the hardest. So take some time with this. All right. Okay, let's take a look at this piecewise function. I think I want to do another difference quotient one. But I don't have a space to do it. I will make sure to do a difference quotient one at the start of the next video. I don't want to waste the time now, but I will, because I think it's important for you to see that again. So if you need to see another one, go to the next video and look for that definitely before you do your homework. You'll be watching all of these before your next homework anyway, but it's important to see another one. I don't know why I didn't put that in the notes. Okay, piecewise functions is our next topic for this particular part of the notes. It is a function that is defined by two or more equations over specified domain values or intervals. That is a piecewise function. When we looked at that merchandise versus shipping and handling example on page 5 of these notes, let's scroll back up here. This right here is a piecewise function because it has different equations for different parts of the domain. So for the domain between 0 and 6, the function value, between 0 and 15, the function value is 6. For the domain values between 15 and 30, the function value is 8, and so on. Okay? So we definitely have a piecewise function here. Different parts of the domain have different equations describing it. Let's go back down here. Here is another example of that. For x less than 2, we want to use this equation, f of x equals x squared minus 1. Now, for the part of the domain where x is greater than or equal to 2, we want to use 2 minus x. A lot of you probably have, if you don't have unlimited data on your cell phone, you probably have a piecewise function determining your cell phone bill. Up to, let's say, 10 megs of data or whatever it is, you probably pay a certain fee. And then after that, for a different part of your domain, amount of data used, you pay a different amount. So there's definitely piecewise functions all over the place in the real world, okay? Let's see how we evaluate this. F of 0. That's talking about my x value being 0. That fits in this category, right? X less than 2. That tells me I want to use this equation to evaluate that. And I plug in 0 into that equation because when x is 0, I am using that equation. So I need to use that equation and plug in 0. Now for part B here, I am looking at a different scenario because I'm looking at x being equal to 2. Well, that fits in this category for x being greater than or equal to 2, right? That equal sign on here tells me I need to now, for x equals 2, use this equation and plug in 2, and I get 0. That also tells me a couple of things about ordered pairs. When x is 2, y is 0. That ordered pair will be on the graph of this function. Here, when x is 0, y is negative 1. That ordered pair will be on the graph of this piecewise function. Let's look at f of 7. Take a minute to think about which equation do I want to use here, the top one or the bottom one? When x is 7, I want to use the bottom one because x being 7 fits in this category for x greater than or equal to 2 because 7 is greater than or equal to 2. So I plug my 7 in there and I get the ordered pair 7, negative 5 is on this graph of this function. Now it asks us to actually graph the function down here. I am going to, so I don't have to keep scrolling back and forth, I'm going to write this here so we can see it. X. Okay, so let's graph this. We have a couple of points. Should we just plot those points? 0, negative 1 is here. We have 2, 0. X is 2, y is 0 there. We have 7. 1, 2, 3, 4, 5, 6, 7. Negative 5. 1, 2, 3, 4, 5. Here. Okay, that's what we have. Well, That doesn't really tell us a whole lot, because this thing being defined by different equations could have an interesting graph. Let's start with this part right here. Okay, we are thinking of that as y equals 2 minus x. Many of you may remember that that's actually a line. We're going to get into that, like I said, more in the next unit, but this is actually a line, so we want, so we can graph it however you're comfortable graphing that. If you're comfortable graphing lines at this point, then go ahead. If not, then let's just do a table of values to figure out what this looks like. Let's see, we only want to consider values where x is greater than or equal to 2, right? So we might do 2, 3, 4, 5. It would not be appropriate to plug 0 into this equation, because when x is equal to 0, we should be using the other equation. So let's see here. 2 minus 2 gives us 0. We already knew that. 2 minus 3 gives us negative 1. 2 minus 4 is negative 2. 2 minus 5 is negative 3. So let's plot those points. 3, negative 1, 4, negative 2, 5, negative 3, and we know we're going to hit that point. So I think it's pretty safe to graph this line for that part. Okay? We do not continue to the left here, because this line that I have in purple, circled in purple, only applies for x values greater than or equal to 2. The equal sign on there tells me I have a filled in circle at that point, 2, 0. Now let's talk about the other part of this. Let's do in green, some like Joker colors going on here. We're going to be looking at y equals x squared minus 1 for x less than 2. And we'll do the same thing. We'll do a table of values here for now. By the end of this unit, by the end of the next unit, you'll know that this is what we call a parabola. But for now, let's take a look, plug in some values. I definitely only want to plug in values less than 2. But the problem that I'm running into is I want to know what's happening at like 1.999, right? So I'm actually going to plug 2 into this. That will give me a y value of 3. Let's make a note here. This has to be an open circle, because I don't actually want to know what's happening. This function doesn't apply when x equals 2, but it does right next to 2. Like 1.99999, it does apply for that. And so that's why I'm going to do an open circle there to tell me to go right up next to that, but not actually at that point. And then we can do some others. 1, 0, negative 1, negative 2, maybe just to see what's happening. When I plug in 1, I get 0. When I plug in 0, I get negative 1. When I plug in negative 1, I get 0. When I plug in negative 2, I get 3. All still okay as a function, because I only get one number out when I plug that signal value in. Okay, let's plot these. Go back to black, because I want you to remember that it is all one function. We just define it by different equations. So 2, 3, we said had to be an open circle. 1, 0 here. 0, negative 1 we already had. Negative 1, 0. Ooh, it's starting to curve back up. Negative 2, 3. There. So what we have is this curving thing. Like I said, this is called a parabola. We're going to talk more about these later. And I put an arrow on both ends of this, the parabola on the left end and the line on the right end, because it continues on forever. because there's no restriction on x less than 2. That means x, could be negative a million, or x greater than or equal to 2, x could be 3 million, right? So that's why we have the arrows on there. That is what this piecewise function looks like. Okay, you just break it down piece by piece, but you don't graph this entire parabola. You only graph the part of it where x is less than 2. And you don't graph this entire line. You only graph the part of it where x is greater than or equal to 2. Okay? Okay, let's take a look at an example, an application of this. For a 3-day rental, a car rental company charges $60 for the first 300 miles. If you go over 300 miles, they charge 15 cents per mile. Write a piecewise function describing this situation and determine the cost if you drive 335 miles. Okay, so I'm thinking about this. 3-day rental, a car company charges $60 for 300 miles. And then they charge 15 cents per mile. This isn't quite clear. They charge 15 cents, let's say additional per mile. So we still have the $60 plus 15 cents per mile for over 300 miles. All right. So I would say the easiest part of this, I'm going to call this, maybe P of X for the price. You do C for cost. We definitely know, we definitely want X to represent the number of miles, right? Because we have a cost per mile here. So we have a change depending upon how many miles we have. Our price for this car rental is $60 if X is less than or equal to 300. That's it. It's just $60 if X is less than or equal to 300, where X is the number of miles. Now, if X is greater than 300, we have that $60 plus we have to add 15 cents per mile. So you have to do 0.15 times X because that'll be your cost. Oh, shoot. Not quite, because that would charge you 15 cents per mile over 300 is what I really meant. So we're going to have to do X minus 300 there because you only want the 15 cents for the miles over 300. Okay? So the X that's what I meant. I don't think that's exactly clearly what I wrote there, but that's what I meant, is anything over 300 miles, you want 15 cents per mile. Well, if you drove 350 miles, you only want the 15 cents for those 50. So that's why we have to do X minus 300, where X represents the number of miles. Okay? Now, to answer this question, determine the cost if you drive 335 miles. What's your price for 335 miles? Well, we clearly have to use this bottom equation because it's over 300 miles. So we're going to do 60 plus 0.15 times 335 minus 300 and simplify that. $60 is your flat fee. 15 cents for the 35 miles that you go over that threshold, right? 35 times 0.15 is $5.25. So you have $65.25 would be your total cost for 335 miles. think that's a good place to stop. We talked about the difference quotient and piecewise functions in this video. The next video is going to talk about increasing and decreasing functions, and then minimum and maximum and even and odd functions. And that'll wrap up this part of this unit. Okay, then we're going to get into linear functions. But for now, that'll wrap up this part of this unit. The next video will. Okay.